Welcome to the video for the exercise that we did, the classwork on exponential expressions for the Math 050 class. First of all, we started off with our do now, where we just did some calculations. First of all, 2 times 4 plus 3, that is really 2 times 7, which is 14. Second one we did was 2 times 4 plus 3. So same thing except without the parentheses. It sounds the same, 2 times 4 plus 3. But this time we do 2 times 4, which is 8. And then we add the 3. Which equals 11. And the last one we did was 2 times 4, and then we added 2 times 3. So we did 8 plus 6, which equals 14. What we found was that this calculation and this calculation give us the same results. So we concluded that you can add it within the parentheses first and then multiply, or you can multiply by both of the numbers that are added and get the same answer. And we did that in rules. If we look down at the rules down here, C times the quantity A plus B equals C times A plus C times B. Then we did our calculations with the exponents. We had 4 times 3 to the second power. To do that, because of the brackets say to do the 4 times the 3 first. 4 times 3 is 12. So we'll take 12 to the second power, which is 12 times 12, or 144. And the second one we did does not have the brackets. It's just 4 times 3 to the second power. And since we do exponents first, the first thing we do is 3 squared, or 3 times 3, which is 9. That gave us 36. Then the last calculation, we have 4 squared times 3 squared. So it's similar to the distribution that we did in the the left side of the exercise. So now we have 4 squared, which is 16, times 3 squared, which is 9. And that also gives us 144. So we can write that in terms of our rules. Once again, we notice this one and this one give us the same answer. So we can multiply first and then square it, or we can square both of them first and then multiply. We get the same answer. And we write that with our rule in this way. A times B to the C equals A to the C times B to the C. Then we went on to our classwork, which where we were rewriting exponential expressions to see what conclusions we can draw. The first one was the exercise where we multiply 2 exponential expressions together. So 5 to the third power is an exponential expression. It means 5 times 5 times 5. And then we multiply that by 5 squared, which means 5 times 5. And that gives us 5 5s that are multiplied together. We can rewrite that as 5 to the 5th power. And then I wanted you to check those answers. 5 to the 3rd power means 5 times 5 times 5. That's 125 if you put that on your calculator. And 5 squared is 25. So then we do 5 to the third power times 5 squared, or 125 times 25. Which gives us 3,125. And if we go to our calculator and actually do 5 to the 5th power, it's going to tell us that is 3,125. We could do the same thing with the next one. So 5 threes multiplied together, 3 threes multiplied together. How many threes is that all together? Why don't you pause the video for a moment, go through that same exercise with the 5 to the third power, 3 to the 5th power and 3 to the third power. When you come back, we will kind of summarize that. So pause the video now, please. Okay, now that you have looked at that, hopefully you found if you write 5 threes and 3 threes, you will have written 8 threes. And if you do 6 twos and 4 twos written out, you will actually have written 10 twos. So this is like 2 to the 10th power. And the last one, 3 times 3 times 3 times 3. And then 2 times 2 times 2. We can't really do anything with that because they're different numbers. The bases are different. 3 is the base and 2 is the base. They're different. The 4 and the 3 are the exponents. So we cannot add exponents if the bases are different. But in our rule, we can say a to the b times a to the c. That means the bases have to be the same. They're both a. They're both the same number. They're just raised to 2 different powers. And we can see that we just have to add the powers, b plus c, to get our new power. So if we're multiplying 2 exponential expressions with the same base, we can add the exponents. Next one is dealing with raising an exponential expression to a power. So I have 2 to the third power and that entire expression to the second power. So I'll start off with 2 to the third power. And that's 2 times 2 times 2. You'll have to trust me, that's a 2. And I want to square that. So if I square it, I multiply it by itself. So I take that 2 times 2 times 2, and I multiply it by another 2 times 2 times 2. So I end up with a total of 6 2's. Because I have 3 2's multiplied together, and then I multiply that by itself. And if I think about that, I'm going to check that. 2 to the third power, you put that on your calculator, that's 8. And so then if I do 8 squared, that is 64. And if you go to your calculator and do 2 to the 6th power, 2 to the 6th power you will find is 64 also. Go ahead and try the other ones and then see what conclusions you can draw from that. Pause the video for just a moment. When you come back, we will discuss it. Okay. Now that you have looked at that for a moment, hopefully you notice that in the second one, you write 5 threes, but you have to write that 3 times because it's to the third power. So you actually do 15, 3 to the 15th power. So when we write our rule, we're going to say a to the b times c. And b times c, we just write b with a c next to it, since they're both variables. So when you raise an exponential expression to a power, you multiply the exponents. Next, we're going to look at division when we're dividing exponential expressions. So rewrite each exponential expression without exponents, then rewrite that expression with a single exponent. Use a calculator to check your work. So the first one, I have 5 to the 5th power. So that means write 5 5s and multiply them together. And in the denominator, I have 5 to the 3rd power. So I'm going to write 3 5s and multiply them together. And now if I think about it, I have 5 in the numerator, 5 in the denominator. I can reduce that by dividing them both by 5, or I have 5 divided by 5. That's 1. We say we cancel it, we cross it off, but really it becomes 1. This becomes 1 as well, and this becomes 1 as well. If I multiply 3 1s together, I still get 1. And then I multiply that times 5 times 5. 5 times 5 is 5 to the 2nd power. So when I have 5 to the 5th power divided by 5 to the 3rd power, I end up with 5 to the 2nd power. And if we look at this, 5 to the 5th power is 3,000. Yeah, we just did that. What was that? 5 to the 5th power was 3,125. And 5 to the 3rd power was 125. And if we divide those in our calculator, we get 25. And then if we try 5 to the 2nd power, 5 to the 2nd power, we put that in our calculator, we do get 25. So try that same example, same exercise with the other problems there. And pause the video just a moment. When we come back, we will discuss the conclusions that you can draw. Okay, thank you for pausing the video a moment. Now that you're back, hopefully you noticed you write 4 3s in the numerator, 3 3s in the denominator. Sorry, 2 3s in the denominator. You canceled 2 of the 3s, so you wrote 4, you canceled 2 of them. You're left with 4 minus 2. Here you wrote 7 2s in the numerator, 2 2s in the denominator, so you canceled 2 of the 7 2s. You're left with 5. And once again, if you have 2 to the 7th in the numerator and 5 squared in the denominator, you cannot cancel anything. So this only applies when you have the same base. The base in the numerator and denominator is 2, or as long as they're the same. So we can say that using variables by using a to the b power over a to the c power. So the bases are the same. When we use the same letter, that means the bases have to be the same. That is going to be equal to a to the b minus c. Okay? So when you're dividing exponential expressions with the same base, you subtract the exponents. We're actually going to do that. I'll go through this really quickly. We're going to do that to investigate some other things. So in this case, we have 5 to the 3rd power, which is 3 5s in the numerator, and 5 to the 5th power in the denominator, So we have 3 5s multiplied together in the numerator and 5 5s multiplied in the denominator. We can divide the 5s again, canceling 3 of them. So now we have, once again, 2 5s left over, but those 5s are now in the denominator. So I have 1 over 5 to the second power. If I look at our expression or our subtraction rule, though, I can subtract the exponents. So I have 5 to the 3 minus 5, which equals 5 to the negative 2 power. So we know that negative exponents mean reciprocal. 5 to the negative 2 is equal to 1 over 5 squared. They mean the same thing. And you can try that with the 8s also, but what you will find is a to the negative b equals 1 over a to the b. So if you want to write it with positive exponents, you put the expression in the denominator. We're also going to use the subtraction property again here. So 7 to the 7th power divided by 7 to the 6th power. 7 minus 6 is 1, so that's 7 to the first power. And if I put it in my calculator, I get that expression is equal to 7. 7 to the 7th power divided by 7 to the 6th power is equal to 7. Same thing with the 4s. 4 minus 3, I get 4 to the first power. And if I put it in my calculator, 4 to the 4th power divided by 4 to the 3rd power equals 4. So we know that a to the first power equals a. Any number to the first power equals a because of the subtraction rule. Now we're going to do something a little different. Well, it's not a little different. It's a little more interesting, but we do the same thing. We're going to subtract the exponents. So I have an exponent of 5 and an exponent of 5. This gives me 5 to the 5 minus 5, which is 0. If I put it in my calculator, though, 5 to the 5th power divided by 5 to the 5th power equals 1. I do the same thing with the 9s. 9 to the 7th power, I subtract 7 minus 7, I get 0. If I put it in my calculator, 9 to the 7 divided by 9 to the 7th is 1. So I can say that a to the 0 power equals 1. It does not matter what a is. Anything to the 0 power is equal to 1. Now that we've done that, we're ready for our group work. The group work, we want to do a lot of things with the with scientific notation. And if we put these in our calculators, 3 times 10 to the 3rd, scientific notation really means we're saying a number times 10 to the 3rd. This ends up being 3,000, because if I multiply by 3 tens, that puts 3 zeros on the right side of the number. And likewise, 5 times 10 to the 8th is 5 with 8 zeros. One, 2, 3, 4, 6, 7, 8. So it's actually 500 million. And if we put 7 times 10 to the 19th in our calculator, most calculators will say 7e 19. And as you might guess, that just means 7 times 10 to the 19th. Some of your calculators actually say times 10. Some of your calculators use a small e. But when your calculator does things in scientific notation, it will tell you that. The last two numbers will be the exponent, and what comes before it is the number that you multiply times 10 to that power. So if we do calculations, I can think of this calculation, 3 times 10 to the third times 3 times 10 to the fifth, I can multiply the 3's first and get 9. 3 times 3 is 9. And then I multiply 10 to the third times 10 to the fifth. And since they have the same base, all scientific notation is with a base of 10. I can add the exponents. 3 plus 5 is 8. And likewise, when I have 2 times 10 to the 7th times 4 times 10 to the 9th, I can multiply the 2 times the 4, get 8. And then 10 to the 7th times 10 to the 9th, the bases are the same. So I can add the exponents, and that's 10 to the 16th. And some of your calculators will actually do that in scientific notation because they don't have 16 places on the screen. Everybody's calculator should do scientific notation on this one. Because we have 6 times 4, which is 24. Times 10 to the 13 plus 15. 13 plus 15 is 28. If you do it on your calculator is actually going to say 2.4 times 10 to the 29th. When we do scientific notation, we want this number to be between 1 and 10. So what I did, I took the 24, I divided the 24 by 10, and to compensate for that, to make up for that, I multiplied by another 10. So I divided by 10, divided the 24 by 10, and I multiplied this by 10. That gets my 2.4 between 1 and 10, and it doesn't change the number because now I have another 10 that I'm multiplying by. Okay. So if we write a rule for scientific notation, a times 10 to the b times c times 10 to the b equals a, c, we multiply those numbers, times 10 to the b plus d, except that sometimes we may have to divide the AC by 10 and then add 1 to the b plus d. The next thing we're going to do is divide scientific notation. So I have 3 times 10 to the third divided by 3 times 10 to the fifth. So I have 3 divided by 3, which is 1. And then I have 10 times 10 to the third divided by 10 to the fifth. Okay. And since I'm dividing, I can subtract the exponents. So this equals 1 times 10 to the negative 2. And with scientific notation, we always use negative exponents. We never use fractions. When we have negative exponents, if the exponent is positive, we use a positive exponent. But we wouldn't say 1 over 10 to the second power. We would say 1 times 10 to the negative 2 power. Okay. So likewise, when we have 2 times 10 to the 9th divided by 4, we get 0.5. 2 divided by okay. There's a point. 2 divided by 4 is 0.5, and I have 10 to the 9th divided by 10 to the 7th, which gives me 10 to the 2nd power. So I have 0.5 times 10 to the 2nd, but I want that 0.5 to be between 1 and 10. Times 10 to the minus 2. So I multiply this by 10. I multiply the 0.5 by 10, but that means I have to divide by another 10. So I actually get 5 times 10 to the minus 3 to be in correct scientific notation. Likewise over here, 4 divided by 6 gives me 0.667 times 10. And if I subtract that, I get negative 38. But if I put it in the calculator, I get 6.67 times 10 to the negative 39. So if I write my rule, a times 10 to the b divided by c times 10 to the d, and you notice I put it in parentheses because I need to multiply first and then divide. If I divide first and then multiply the answer, I get a very different number. So I do a divided by c times 10 to the b minus d, except that sometimes I may need to multiply the quotient by 10 and divide the exponential expression by 10, or subtract 1 from the exponent. The rest of the group work you kind of have worked on your own. That's estimated that there are 10 to the 80 atoms in the known universe. Scientific notation is much better for this because we don't want to write 80 zeros. It's a really big number, but we can actually get a handle on it, get an idea about it by using the exponential notation. Okay. So go ahead and finish the rest of the sheet, and then do the applications and turn them in. Thank you very much.